In this video, we want to start looking at what's called an improper integral. So the word improper in math, doesn't necessarily mean bad, like the typical connotation. If you think of improper fraction, right, that's just a different type of fraction. We use improper fractions all the time. So they're not bad. They're just, they're kind of different from the norm, right? The norm for a fraction is to write it as the numerator less than the denominator, and otherwise you use a mixed number like 1 3/4 or something like that. So same idea with integrals here. It's not something that's bad. It's just something that's a little bit different from the norm. So the norm for us so far for integrals has been to look at a definite integral with finite bounds. And we've kind of been avoiding areas where the function would go to infinity. So for example, we might look at something like the integral of 1 over x from 1 to 3, right? And if we did that, we would get the natural log of x from x equals 1 to x equals 3. And then we would get the natural log of 3 minus the natural log of 1, which is 0. So ultimately, we get the natural log of 3. Now, we've avoided things like the integral of from 0 to 3 of 1 over x dx. Okay, so think about what this would be. If we just think about this on a picture, why this is different. Okay, so 3, let's say it's right here, it would be like the 0.3 1/3. But as we get closer to 0, that area that we're looking for here, this is, it's blowing up, right? So there's an infinite amount of space here that we're integrating over. So this doesn't necessarily imply that the actual area under this curve is going to be infinite. It could be, but it could also be finite. Okay, so we're going to see something similar when we start looking at infinite series. In infinite series, we'll see that you can add an infinite amount of terms together and you'll still end up getting a finite answer. Okay, so how does that work with integrals though? How do we deal with infinity? Well, the big way that we've seen of how to deal with infinite things so far is the limit, right? That's how we define the derivative, which is the limit so that you have infinitely close points. That's how we've defined the area, so that we have an infinite number of rectangles under the curve, right? So no different here. We want to come back to this idea of the limit to help us take the integral of like an infinite area. Now I want to come back to this one in particular. First, I want to look at what happens when the bounds are infinity. Okay, so this is another thing we can do. We can take the limit from 0 to infinity of something. Okay, so let's do 1 over x dx. So again, the picture of this, it looks similar to that one. It's just going the other way basically. So if 1 is like right here, the 0.11, then we're looking for this area. Okay, so we can see that this area, while we're going all the way out to infinity, the area is going to get really, really small, right? So it's possible that it will converge to a finite number, but we need to look mathematically to see if it will or not. So what we can do is when we get to the point of evaluating this infinite bound here, what we can do is we can instead, we can't just plug in infinity, but we could just plug in some number, like some kind of dummy variable, and then look at the limit as that variable goes to infinity. Okay. So we'll rewrite this as the limit as b goes to infinity of 0 to b. Of course, you can use whatever letter you want, but b is typically used for the second bound of integration. A is used for the first. And then we're going to have to keep bringing that limit along with us. So it gets kind of annoying to write every time. But we need it for this to be proper. Of the natural log of x We can drop the absolute value here because we're only looking at a part where this is going to be positive anyway. From, oh, I'm sorry, this should be from 1 to infinity, right? I meant to say from 1 to infinity. That's why I drew this as 1 right here. 0 to infinity, then we're looking at infinite area to infinite area. So I want to start from a finite place and go to an infinite place first, okay? So this should be from x equals 1 to x equals b. And then we're going to just keep going. We'll keep bringing that limit along with us. Limit as b goes to infinity of the natural log of b minus the natural log of 1, which is just 0, so we can forget about that. And now the limit as the natural log goes to infinity, this is going to be infinity. Okay, so here we don't end up with a finite area. So I said we could, we didn't in this case, but this is what we need to do to determine whether or not we're going to end up with a finite area. Okay, so let's look at another example and see what happens. So here we're saying that the area under the curve is infinite. And by the way, when this is infinite, we say that original integral, this one right here, we would say that it diverges. Okay. And if it goes to a finite number, we would say that it converges. Okay. We'll see that same terminology again when we start talking about infinite series. So let's do a closely related example. We're just going to change the inside function a little bit. We'll change it to 1 over x squared. Okay. So you can already imagine how this is going to change it a little bit. We're not going to have the natural log as the antiderivative. We're going to have a fraction. So it's possible that we'll end up with a finite answer this time. All right, so what we're going to do is exactly the same thing. Just our antiderivative will be a little bit different here. Okay, so we're going to take the limit as b goes to infinity from 1 to b of 1 over x squared dx. So we'll get the limit as b goes to infinity of, what is that, negative 1 over x. And then we're going to evaluate this from x equals 1 to x equals b. And then we're going to put the bounds in, and then we'll take the limit. Okay, so negative 1 over b minus a negative 1 over 1. So those will cancel. We'll have a positive. So essentially we have the limit as b goes to infinity of 1 minus 1 over b. So of course when we take the limit of 1, we just get 1. But when we take the limit of 1 over b, this is going to go to 0. So ultimately we're going to be left with 1. Okay, so in this case we do get a finite answer. So you might start to think about why, right? So like, why do we get a finite answer in the 1 over x squared case versus the 1 over x case where we don't? Okay, because they're really not that different. And we're going to see this come up again in the infinite series again when we look at the series of 1 over x versus 1 over x squared, and we're going to see the same result. And the reason is basically that 1 over x squared, it gets smaller quicker, right? If you just think about like the integers, if you look at the sequence of like the terms, you have 1, then 1/4, then 1/9, then 1/16, then 1/25, right? Whereas with 1 over x, you have the numbers 1, 1/2, 1/3, 1/4, right? So 1 over x squared gets smaller a lot quicker. And that ends up making it converge to a finite number. So this we say, like I said, converges. Specifically, we might say that it converges to 1. Okay, diverge implies that it goes to infinity, so we don't say it diverges to anything. Maybe to infinity or negative infinity, I guess. So before we go on to more examples, I do want to mention, why this idea is very important. This comes up in probability and statistics all the time because we're working with probability distributions, which might be defined on an infinite domain, right? Namely, like something like the normal distribution, for example, right? The normal distribution, the bell curve, um, it is defined from negative infinity to infinity, right? And in order for something to be a probability distribution function, the area underneath it has to total to 1. Just like with a discrete distribution, all of the probabilities have to sum to 1. Same thing with a continuous distribution, the area under the curve has to be 1. And in order to find that area, we need an improper integral because we have to integrate from negative infinity to infinity. Okay. So this is very important in probability theory. It comes up pretty much with any continuous distribution that you can think of. So let's look at an example now with, let's look at one with both bounds being infinite. So here we're going to look at the integral from negative infinity to infinity of x e to the x dx. So in general, rather than like doing it as one big integral and taking two limits, it's usually better to break it up into two different integrals. So the typical way we like to do this is by integrating from negative infinity to 0 of x e to the x dx, and then integrating from 0 to infinity of x e to the x dx. The reason it's typically done like this instead of just calling the bounds a and b and taking the limit as a goes to negative infinity and b goes to infinity all at once is that when you have two limits like that, it's not a trivial matter to decide which one has to go first, and whether or not you can interchange them. In this case, there really wouldn't be an issue with it. So, I mean, if you try to do it that way, you're probably not going to run into any issues. But in general, it's not something that we can assume for any function and for any limit. So it's usually, just to be safe, kind of is the reason, I guess, would be to break it up like this, and then we only have to take one limit of each of these. Okay. So with negative infinity to 0, like I said, we typically call the lower bound a. So we'll take the limit as a goes to negative infinity of a to 0, x e to the x dx, plus the limit as b goes to infinity of 0 to b of x e to the x dx. Okay. Now x e to the x, we did a similar one in the integration by part video, but as you might expect, you do need integration by parts for this. So let's just do the integral itself on the side here. So then we don't have to keep rewriting this every single time, right? So a nice way to kind of, keep track of this is maybe you label this as like 1, and then you refer back to 1 later on, just to kind of make it clear. So here we're going to let u equal x. Whoops. Which is going to make du equal to dx. And then we're going to let dv equal e to the x dx, which makes v equal to e to the x dx. So this is equal to x times, this would just be e to the x. So this will be equal to x times e to the x minus e to the x du, which is dx. Okay, so remember it's u times v minus the integral of v du. So luckily that's a pretty easy integral, right? Just e to the x. So now we'll refer back to 1 here. So then 1 is going to be equal to the limit as a goes to negative infinity of x e to the x minus e to the x evaluated from x equals a to 0 plus limit as b goes to infinity of x e to the x minus e to the x from x equals 0 to x equals b. Okay. So finally here, we can evaluate the bounds. So we'll plug in 0. So this first term would just be 0 minus 1. So we'll have minus 1 minus a e to the a plus e to the a. And then we'll deal with the limit in a second here. I think we're going to need L'Hopital's rule. Or maybe not. So then we'll do b e to the b minus e to the b, and then minus 0 minus 1, so plus 1. Okay, so now we'll deal with the limit. So another trick with these is that if any individual term is going to infinity, then the entire thing is going to be going to infinity, right? The whole thing is going to be divergent because there's no like getting an infinity for this e to the b, for example. This is going to be infinity, right? And e to the a is going to be, well, that's going to be e to the negative infinity, so that'll be 0. But anyway, my point is that if we get infinity and then we get it like a minus infinity somewhere else, they don't cancel out, right? Infinity minus infinity is an indeterminate form. There's no way to cancel those out. So if we see that any term is going to be infinity and there's no way for us to like rewrite it or use L'Hopital or anything like that, then the entire thing is going to be divergent. So in both of these cases, we're going to get some indeterminate forms. So we're going to have to rewrite it using L'Hopital's rule. So I would encourage you to just go through it and try it. When you come out of it, this one you should get -1 for when you do L'Hopital's rule. This one you can rewrite with L'Hopital's rule because you will get infinity minus infinity here, so indeterminate form, so you should rewrite it and use L'Hopital's rule. But ultimately, when you come out of it, you're still going to get positive infinity. Okay. So ultimately, we'll just get that this is divergent. Okay. Now, this does tell us, you know, just for future reference, if we had something like this, this would have been -1. Okay. And this is kind of common with e to the x if you have like a negative infinity, or if you have e to the negative x and you go to infinity. A lot of times those end up being convergent just because of you know, the nature of the exponent there. Okay, so this is what we do when the bounds are infinity, and then in the next video we'll look at what happens when we pass over a point that blows up at infinity, like for example 1 over x from 0 to 3 or something like that.